and good afternoon. I think we are still alive after lunch and for this wonderful session as stage already set by our narrator. And I would like to say here particularly, respected distinguished guest, eminent panelist, colleagues from semiconductor fraternity, and my friends. I welcome you all on this vibrant topic which has been decided as Advantage India for Compound Semiconductors. Particularly, compound semiconductor used to be considered as a similar process as good as silicon and considered to be less complex as compared to the silicon. But it is true in terms of number of layers if you talked about, seeing the complexity of the silicon CMOS technology as told by the previous speakers. But of course, there are many challenges in compound semiconductor technology itself, particularly when we call that wide bandgap semiconductors. And around the globe, many kind of a product are being used. And as in the morning, in the discussion has been told that India will be touching in the semiconductor technology of a business of around $110 billion. Out of that, 13% would be the share from the compound semiconductor itself. And if that is so, then we cannot leave this stone unturned to touch the compound semiconductor technology and to see what are the opportunities, what are the advantage in setting up the compound semiconductor technology in India. As we all know, sir, transistor has celebrated its diamond jubilee, 75 years of completion since its invention. So as India, 75 years and we are in Amrit Kal. And government already has laid down the red carpet for the investment in the semiconductor technology domains. And they are open every channel to establish a right conducive ecosystem, sir, within India so that we can ask the people to come and invest for the same, to fulfill the requirement. So to start with, I would like to introduce with my panelists here today, starting with Shri Vivek Sharma, who is a Managing Director of STMicroelectronics and responsible for India overall operations and driving strategic initiatives in the country. He also has an additional responsibility of Group HR, APEC and China region. Everybody knows ST is one of the growing microelectronics manufacturing as well as design house, who's having a total revenue of $16.2 billion in 2022, serving globally across the various domains of the electronics sector, but they also having a tagline, reducing the carbon footprint, and they are targeting it to reduce it by 2027. Vivek has been with the STMicroelectronics over 30 plus years and has served in the diverse functions and leadership and at various positions in STMicroelectronics. And he has been instrumental in setting up various design centers in India. Of course, he is also associated with various electronic memberships around the globe. I feel delight to introduce him in the Semicon for this panel discussion, sir. Welcome, sir. Next speaker is Dr. Chang Yee Shyi. He need not to have any introduction. Sir, you are a pioneer in the technology. He is a real educationist in the field of semiconductor technology, spent over 30 plus years in the education and research. He started his career and he has a 200 of patent under his belt. Because of his long career in the education, Taiwanese government has given him an award for education by Education Ministry. Dr. Chang has a illustration careers in particularly government organizations also. He is a minister of Congress and he holds the position in the European committees also. National Federation Industry membership and Technology Ambassador for the Indian Cellular Electronics Association. Dr. Chang's acumen extended beyond the academia having founded more than 10 high-tech companies and that have achieved listing status. Apart from this, he has been a visiting professor at UCLA and University of Illinois. He has been instrumental in shaping the Taiwan economic and technological landscape, promoting to the next level. And he, not only in this field, he is the person who is responsible for setting up world first 6-inch compound semiconductor facility in Taiwan. Sir, congratulations. And we are honored to have you here, sir. Apart from that, he has also established a 4-inch compound semiconductor facility in Taiwan. Then he also has experience in the field of equipment manufacturing. You name what process, what equipment. He has a hold and in the advisory board of various equipment manufacturing companies like Applied Material and so on. Currently, Dr. Chang is an executive director of Taiwan Vajai Health Management International Holding, partner at Imperial Industries and General Advisory of Taiwan, Optoelectronics Technology, and Industry Development Association, among other roles. His work continued till date to propel advancement in the science and technology for economic policies. I cordially invite you, sir, for this panel discussion. Thank you to be here, sir. Mr. Rohit Girdhar is from Infineon. He is a vice president and senior director at Infineon Technologies. Under his leadership, Infineon works on various strategic assignments for Asia-Pacific regions since April 2017. He is also a board of member of Infineon Technologies India Private Limited. He started his professional career in 1998 at Teradyne Inclusive, California, as a project manager. Later, he moves to GE. Mr. Rohit holds a bachelor degree in the engineering from BITS and holds a master's degree from Stanford University, as well as a MBA from INSEAD. He has been motivating force behind making Infineon Technology a global semiconductor leader and innovator in the emerging field of semiconductor device used for power system and Internet of Things. I sincerely welcome Rohit for this panel discussion. And I know Infineon is the only company who is working in silicon domain, gallium nitride domain, and silicon carbide domain, and covering all the aspects of power sector. So we need a lot from you, sir. Mr. Sriram Ramakrishnan, CEO of Business Head Reliance Power Electronics Limited. You are a builder, sir. You are a businessman. You are a leader. You are a team builder. Years have a experience of proven business development by M&A and organically by innovating across the power electronics value chain, including R&D, manufacturing, marketing, sale, and services. Built the largest Indian UPS company, Consol Neowatt, before acquisition of Fusey Electronics in 2019, the largest power company MNCs in Japan. Now, heading as Reliance Power Electronics Limited on the mission to build a world-class team and business in the field of power conversion and energy storage system to accelerate energy transition in India and globally. It is a wonderful to have you here, sir, for this panel discussion. And of course, you are not out of the box. We need a lot from you because you are an investor. Darshan Hiranandani, Managing Director and Chief Executive Officer. Sir, Darshan Hiranandani and leads the two verticals of Hiranandani Groups. One is H Energy vertical and another is Yota. Yota is working as a data center company. He holds a master degree from RIT USA and he is a member of advisory board in RIT USA as well as RIT Dubai since its inceptions. He is also having a membership in the charitable institute who is running the colleges in India and having almost 30,000 students in the Mumbai city for the same. Under his leadership, H Energy has ventured into LNG regasification, terminal and neutral gas pipeline project in India and supplies natural gas to customers in India as well as in Asia. Darshan started his professional career pioneering the development of 23 Marina in 90-story, 400-meter residential complex in Dubai, and now he is interested in scaling down meter into micrometer. With this, we will start this discussion, sir. Now, house is open, sir, to have a global perspective on the semiconductor technology. We'd like to hear in 5 minutes for each one of you, put your idea. I start with Darshan Hiranandani, sir, to put your perspective straight away that what is your vision and how you would like to go from meter to micrometer. Thank you, sir.
Hello? Hello, yeah. Hooda Saab, thank you for that wonderful introduction, and it's absolute pleasure to be here. And that's a very good description to go from meters to micrometers. My father likes to think in square meters, though. But this is a great beginning. We ventured into, as we moved from a real estate company to infrastructure, then we got into high-tech infrastructure with data centers, and I'm proud to say, in a short time now, we will be probably by the end of this year, the largest data center player in India. And we've gone from strength to strength in that space. And as we started working in more and more technical things, we've started moving forward where by October, we will be launching, which hopefully we will be a completely indigenously developed public cloud platform. I was also proud when I ran into the AMD folk yesterday and they said, oh, you're with Yotta, you guys buy a lot of our AMD servers. I said, that's not a bad beginning to make. But the journey that we're talking about right now is a little different. Having space and having data centers and getting into semiconductors is a very different ballgame. And when we started, hearing about India's semiconductor mission, started hearing about chip shortages across the board, we started scratching our heads and saying, what is exactly happening here? What's the need? What's the gap? What does it take to get into this industry and build it and actually make things happen? And I must tell you, the first beginning happened with my interactions with ISM, where they said, listen, why don't bright groups like yours, you people spend some time and your country's calling, come and deliver. And at first I was a little reluctant, but as we got into a little more detail, we realized some magical numbers. The first part is India is moving and becoming a massive consumer of devices, of technology. And I decided to focus on the niche of power semiconductors. And I said, okay, what's the best generation of technology out there? And we also realized that GaN and silicon carbide are the technologies here to stay. And we said, okay, what does it take to make semiconductors? And I know less than each and every one of you here. So everybody here knows more than me. So, but this is much more of a layman's opinion. And I said, what does it take to make this happen? And I went and visited 12 fabs around the world, visited 30 ATMP companies, had probably 200 interactions with various players. And then we suddenly realized that on a global scale, the only thing missing in India is mindset. There is no other problem that's missing in the country. So the first thing, and the Prime Minister captured it absolutely correctly. Previously, people said, why India? Now the question is, why not India? But I will try and drill that into just a little more detail. So the first interactions I had with people, and they said, it can't be done in India. So I said, show me what you can't do in India. I want to physically go and see it. And I suddenly realized that semiconductor business was broken up into three parts: logic, memory, and power. And I said, okay, logic needs 60 masking processes, memory needs several layers of density, but I think compound power, where we can save a lot of energy and create energy efficiency into the country. And we have found that cars, washing machines, dryers, TVs, mobile phones, all of that is now being assembled and put together in India. There's a role to play out here. And I said, okay, maybe that's the right space to start off. And for people who come from a very high-tech background, 60 steps seem easy. For people who come from an infrastructure background, doing anything in India seems easy. So, we're all looking at it from different sides of the spectrum. But we progressed that forward and we suddenly realized that India has a lot of strengths. Energy, India has great strength. So when you compare to energy costs in Japan and Taiwan, where a lot of these semiconductors are being made, the fabs I visited are spending 27 to 42% of their costs on energy today. I'm talking about running costs, I'm not talking about research. And we think we could bring that down in India by 66%. So they're spending 25 cents per kilowatt hour. We think we can bring that down to 8. People and talent, we think that's again a mindset issue and an effort issue. So from our perspective, we've already made an application with the government. We've tied up with the setup from the US. We've tied up with a partner in Japan to actually be an entire IDM, to focus on getting right from a compound semiconductor fab to an ATMP unit and actually make a final chip. Hopefully in the next month or so, we'll complete our formalities with the government. But we're very excited about this space because, like I said, we think that India can be and will be, while today we don't do innovation yet in a large enough scale in India, but certainly taking innovative technologies and implementing them with high precision in India, that's certainly something that can happen quickly. Thanks.
Yeah, so Darshan, I think this was really inspiring to know that, you're venturing and going to create the infrastructure. And I'm with you. I think, we have all the right ingredients to play in this space. So, but let me talk about the compound semiconductors from a power electronics perspective. So today, when you look at how electricity flows and reaches an end application, it is estimated that 70% of all electricity flows through some power electronic device. But with the increasing electrification, when you look at electrons flowing from the source of generation, which could be a renewable source like solar or wind, and then it flows, for example, into an EV charger and ultimately charges the battery in a car, and that electron then has to be flows through a motor controller or inverter to actually drive the wheels of the car. So the same electron now travels through 300% of power electronics, 3 times. And this is the case if you look at for any application today with increasing electrification. So when the electron flows through so much power electronics, obviously things like efficiency becomes very important. And that is where, looking at compound semiconductors, whether silicon carbide for high voltage devices or gallium nitride for the lower voltage devices, low power applications, makes a lot of sense. And as a power electronic engineer, started my career in R&D, we know that any power electronics design starts with, what is the capability of the device, the power semiconductor device. And with compound semiconductors, you have a lot of advantages, whether it is ability to have higher switching frequency, whether to handle more thermals, and with a higher switching frequency, you can reduce your passive devices like inductors, capacitors, so the power electronic circuit can be smaller, it can be more energy efficient, the thermal management becomes easier with higher efficiency. So definitely, when I look at the future, compound semiconductors is going to play a big role. And already, like I told you, power electronics is the golden age of power electronics, with the demand for power electronics going to skyrocket. And like we heard in the morning session, with India already the 5th largest economy and striving to be the 3rd largest, and with a commitment from the Prime Minister of over 500 gigawatts of renewable energy, I think India is going to be a great market, for power electronics and compound semiconductors for power electronics.
Okay, so both of what you guys said is music to our ears at Infineon. Maybe a quick introduction to Infineon because Manish, you didn't cover that. So Infineon is roughly a 14 billion euro company, 55,000 employees. We have about, I would say, half of our revenue comes from power semiconductors, not all. And out of the power semiconductor revenue, an increasing part is coming from wide bandgap semiconductors. So why is all this happening? So I mean, both of you articulated some of the trends which are actually driving this. So what we see is, for example, electric vehicles taking off in a big way, right? And increasingly, range anxiety and things like this matter for adoption of electric vehicles. And where compound semiconductors help is they are more efficient. You can run them at higher temperatures. You can design more efficient inverters. You can have a combination of inverters for front and rear wheel and so on. So that's one application. But then and this is a mobility application. But then on the industrial side, for solar, for energy storage, for some other applications as well, this is where things like silicon carbide are now making their way in. Again, efficiency, the ability to do one-stage conversion instead of two stages as you would do with traditional silicon, this is what makes it interesting. And then you also mentioned gallium nitride. So gallium nitride is, I would say, kind of the next thing after silicon carbide. And we already see it. I think many of you are already using these very efficient chargers. Nobody carries around those big laptop chargers anymore. Those 65-watt chargers or 120-watt chargers, which usually you can do very fast charging through Type-C to Type-C. Those are all, I would say, wide bandgap enabled. And it's increasingly coming into more and more applications. But the switchover is probably towards the end of this decade. Right? So no matter what, I think the next 10 years and beyond are extremely exciting for compound semiconductors. And I think there's also materials beyond that which my esteemed panelist here would be better positioned to comment on. So yeah, I mean, we are very excited by this. And yeah, and happy to now take this forward with specific questions. Thank you.
Compound semiconductor has two major directions. One is power, which you go to through the wire or the cable. The other way is wireless, remote sending from power amplifier from your handset to base station or your handset to satellite, low orbital, Starlink or web. OneWeb, okay. So that is power stream. That's one part. The other part is information. In reality, the compound semiconductor can be actually using in the 5G, 5.5G, and 6G as a major part to transmit, to add on all the signal, very fast signal, onto this power train. And wireless shooting to satellite, whatever the middle, MEO, LEO, or even the GEO. So from the satellite to the ground station, which 6G, heaven and ground together. Okay. So with this one, how you mixture all this thing with good power added efficient (PAE). If a silicon is only 7 to 9% PAE, means more than 90% energy are wasted when you cannot convert to the EM wave. But using gallium arsenide, aluminum gallium arsenide, gallium nitride, or indium gallium phosphide for the optical fiber communication, they are all major role is their PAE is very high. Like we can go up to 50% to 60%. That means you are 7 times better than the silicon. So pure silicon and compound semiconductor should work together, cooperation, not conflict. So I actually starting from the silicon. And then I joined the UMC 1986, 1987. At that time, before TMC founded. So we actually starting with the foundry model, and we developed the SOP, very strict SOP. So I figure out the compound semiconductor can do the same thing with the real mass production from 1 year, 10,000 pieces for military use, become 1 day, 100,000, which I achieved. I founded the GCS. Now this is a company also called the Global Communication Semiconductor. GCS, red. This logo I drew with the geographic map and put the GCS in center. We actually create a track record of 4-inch wafer fab, become 100,000 per day, later become 1 million. And later I established another company called the GCT. Now become the WIN, W-I-N, which produce roughly 3/4 of power amplifier of each handset. So we already shipped, actually, by this technology, shipped more than 75 billion chips from military use, small part. So the compound semiconductor has a huge advantage and a huge application and a large number to deliver. They have a great thing without too many masks and not ASML, very expensive EUV, okay? DUV, EUV, we use a simple mask. But the physics is different. So power semiconductor, actually compound semiconductor, we actually into communication field, also power electronics, which are very important. I think more and more, especially in India, very hot place. #1 population, nearly 1.5 billion people, very soon, okay? I think that we will use the EV car in the near future. If we can do better infrastructure, when I ask the people, are you going to buy the EV car in India? They said, no. Why? I said, no charging station. So I think the infrastructure, charging station, is our compound semiconductor huge usage. And we will become #1 largest in the world. We should have this mission. Why? Because this charging station, we start from scratch, but we can design, we can directly use megawatt power station. We call the hyper fast charging. Hyper charging station. One charging station, you can simultaneously charge 16 cars. And every 1 second, you charge 1 kilometer. That means if you want to drive 300 kilometers, only 5 minutes. This is our goal. Compound semiconductor, we can reach. Infineon, STMicro.
Let me ask you a question. What is the size of the cable you would need for such a hypercharger? How big will it be?
Oh, the cable is not thick, still less than 500 amps. But the major key is you increase the voltage of silicon carbide. Silicon carbide can raise from present 1200 volt, 1.2, 1.7 kilovolt, and then 3.3 kilovolt, 6.6 kilovolt, and 10 kilovolt. Silicon carbide, you can reach 20 kilovolt, one device. In that way, in reality, for 1 megawatt, you only need actually 3.3 kilovolt. You multiply 500 amps, you already 1 megawatt, right? So in reality, we should resolve chicken and egg problem. We should have infrastructure first to have chicken, and then then you have a lot of egg. Our EV car is an egg. There's no problem. Indians, I think, eat a lot of chicken. Right? So we actually, advantage of India, because we have no burden, because we are starting from white paper, we have no drag force, we have no burden. So we can plan in more faster way, more efficient way, and more low-cost way to build those 1 megawatt or 1.5 megawatt hyper charging station. With this one, you really can enjoy 1 second, 1 kilometer. Even big car is okay. So we will change. our EV car will become IT car. Everything IT, right? With the 17 radar, whatever millimeter wave is gallium nitride, right? Millimeter wave, LiDAR, everything, 20 radar. One EV car will purchase 2,000 US.
So good afternoon to all of you, and really a pleasure to be together with such eminent panelists, and thank you Semicon India for inviting and for your introduction, Manish. To speak about the compound semiconductors, I think we have heard already quite in depth, but let me take a little bit different tour and share with you that how as a company we are leveraging this, and then we will connect it to our Indian situation. So ST, as was mentioned by Manish, we are $16.1 billion. We aim to be $20 billion by 2025 to 2027, depending upon the market conditions. There we have put our company on 3 strategic long-term trends. And if we will see them, we will see that how compound semiconductor is playing a big role there. The first pillar of our strategy is smart mobility. Under smart mobility, we have 3 elements to make, let's say, the vehicles greener, and that's where EV, electric vehicles come into play, safer, and also connected. This is one pillar. But when we are moving, let's say, our vehicles to electric, they will consume electricity. The second pillar of the strategy, though I call it second, but you will see is connected, is power and energy. In power and energy, we are focusing on how to increase the efficiency, and we will see why it is so important to increase the efficiency, and also to tap the renewable energy. So this is the second pillar of our strategy. The third one is related with the IoTs and connectivities. 20 billion IoT devices are there. But once again, even if it is the third pillar, where those IoT devices are consuming the power? From the second pillar. Electric vehicles, again from the second pillar. So the second pillar of power and energy is really the mother. And that's where the whole focus has to be there. And in our company's perspective, as we go further, compound semiconductors, and which mentioned already very clearly, this was known, by the way. Why is such a kind of a big wave about semiconductors? You mentioned 1986, right? The issue with so first, I think the advantage we know is a wider band gap. It can tolerate much more breakdown voltage, higher frequency, 10x smaller size for the same voltage, and so on. So the advantages were well known, but not so easy to manufacture it, right? So we put silicon with carbide or silicon with nitride. But now, great news is that we are moving on that, and this is becoming a reality. That is bringing a lots of opportunity here. Now let's look just on 2 pillars to see how the dimension is. First, in the automotive, the penetration of electric vehicles were less than 10% in 2020. By 2030, it would be more than 35%. So many electric vehicles would be there. Hence, it is going to put the load in the middle. In the middle, world over, they say that 2020 to 2030, in this decade, there would be 30% more electric power needed world over, which is whoppingly high. As per estimates, it is around 24,000 terawatt hour today. We'll go to 30,000 terawatt hour. And if, there are estimates that 40% of this power is consumed by industry. And if there is just 1% more efficiency in the power industry is using, we will save 15 nuclear power plants. This is the impact of it. That's why, no doubt, that why we are looking for solutions, particularly for compound semiconductors, and it is really coming easy there. So hence great opportunity. As ST, we are leveraging it a lot. I believe also Infineon and other companies. And just to share with you that we were doing about $100 billion 4 years back, $1 million. This last year we did 700 million. On silicon carbide itself, that is the kind of penetration this particular technology is having. Now let's look at India. Here we are two-wheeler-wise the world's largest market, 20 million plus vehicles we do that. Four-wheelers around 3 million, but it is going to grow. And if we are going to go towards electric, which we have to, we will again put the burden on our electric generation. We are a little bit, let's say, as per the estimates, we were doing around 1400 terawatt hour, and it will more than double in this decade. By 2030, it would be more than double. So for that purpose, we need to be, and then we are using coal for our generation. So it would be a pity we generate energy by coal and we do not use it efficiently. So hence compound semiconductors, silicon carbide, gallium nitride are really more important, and I would say advantage. We need to convert this particular challenge into the advantage. So we have a challenge. I don't think there is any other way around, but we must convert this towards our advantage. So there I would say one thing, we spoke about ecosystem, which is absolutely correct, that we need to focus on multiple aspects apart from manufacturing, which is in fact definitively we need to bring, but we need to focus. One piece which we miss, some of you who were there in India in 1980s, we used to do lots of system design for analog TV, but then later on, due to opening of the country and IT happening, we lost a little bit edge. We must revive it very strongly to do system R&D. I am very happy that on right side of the panel, I am sure Rohit will be as well, that let's develop the system more and more, and we are there to support, and that piece if we bring in supply chain and everything will work. Yeah? Thank you.
Thank you, panelists, for such a wonderful introduction and set the stage well in the right poise. Particularly, I would like to ask, because since we know all now application segment is set, market opportunity is there. My key question, what would you suggest to Rohit and Dr. Chang that which area India need to focus to start with, whether it is GaN or silicon carbide first or both?
I think we better to put the silicon carbide as a higher priority first, not GaN. Because GaN actually is using silicon base. It's 8-inch wafer fab base. So the investment is much higher. But silicon carbide technology is very tough, but investment much less. That's very important. First thing, silicon carbide, it's not like a silicon. Silicon is opaque. Silicon carbide is transparent. Transparent one, it's like a glass, like this one. That's first thing. Second thing, we use the 6-inch wafer fab. So your investment, $200 million, compared with other things, 2 billion or 5 billion, okay? With this one, but we will get more. Because we have a lot of talent, we need to make skilled labor become skilled talent by technology in packaging, the technology train, to train the more people. The silicon carbide has 7 layers from the growing the crystal, cut, polishing, and this one. And then third layer is how to make substrate. And then is the how to make device. That's fourth layer. And fifth layer is how to do the testing. And then sixth layer is how to do the packaging. The packaging also different because you are passing multiple kilowatt. How come you use a needle? It will go spark. You will be shocked. So the testing, and then you need to make a module. That module is not plastic, actually ceramic, because you are going to pass 200 kilowatt or 1/2 megawatt passing through the module. And with this module, we need to put software and talk to the BMS of each car. And then with this one, actually is 8 layers. But we actually can conclude parallelly every factory, but connected to do high value added. Because silicon carbide, I think, is more expensive than gold. One high voltage one chip you can cost $50, and one wafer you can make 800. So it means huge money, right? You hand carry this one is higher price than the gold. Okay, so if we concentrate this multiple layer, simultaneous of the whole ecosystem, we will get the quick achievement. And we actually concentrate this one. The performance is very high. And with this one, we are quickly can connect with the supercharging station as well as the EV car use and also many, many power usage, especially also the photovoltaic. You know, supercharging station, you can connect with the power storage and then with solar. So we do this one. In the future, hypercharging station number will be 100 times more than the petrol charging or diesel charging. One country, they announced 2 EV car, 1 charging station. You know this one, okay? But if we do the hypercharging, 1 hypercharging equivalent 20 of normal one, we will make economic feasible. And with this one, the turnover and the EV car here, I think India will have 100 million EV car, not 10 million, 100 million four-wheel EV car. You need actually 50 million silicon carbide charger. Another very important final address is the silicon carbide that charging module, when you do the charging station, is consumable. It's not the equipment for 10 years because you have fatigue limited of 10,000 times charging. If your charging station every day charge 50 times, means 200 days, you need to change another board. That means silicon carbide business is huge, become consumable. Thank you.
I think, thank you for that. Maybe to add to that, at least for us, what has maybe some lessons from what we have done in Germany. In Nuremberg, for example, there's a European Center for Power Electronics. And actually at this center, you have systems players, you have semiconductor companies, you have academia. You even have like a PhD day, I think, where PhD students from all over the world actually come and interact with them. So I think you need those kind of watering holes or places for different players to mingle and to discuss new ideas. And this is one example, right, ECPE. But I think they also, for example, institutions have partner programs with countries. So that could be something to look at. Also for those colleagues in the room who are from academic institutions, I think one of the ways to get started would be to do overseas partnerships, I think. That could be one. The second thing is, I think, for students who are looking to do PhDs in this area, right? Yeah, I think there's plenty of opportunities, actually, whether it's within India or also overseas. There's a lot of professors and labs who are looking for very bright young talent in this area of wide band gap, right? So there, I think also there's plenty of opportunities for people to pursue a much more advanced technical career. And I think without a sufficient amount of pool, which is participative in this kind of an ecosystem, as well as doing advanced degrees, you will not be able to build that base. So I think that, in addition to what he said, I would recommend this as well. Thank you. No, that I won't be able to answer. No, so I'll pass that. Maybe you take that.
Actually, I am professor also. At present, you know, or last many years, many graduate, when you ask in India, after you graduate, which job you are going to take? Most are software engineer. But I think when we do the compound semiconductor, we will change the diagram. Because silicon carbide, we will have more job. I just make a simple example. Is a silicon carbide has 7 types defect. One China company, listed company, they only count 1 type, surface type, using KOH to check. But in the middle part, the edge dislocation, screw dislocation, stacking fault, there are 7 different types. all need electron microscope, TEM, cross-sectional, as well as other metrology. Those are our student, our talent, and professor we need to concentrate. They will create a huge number of jobs. What huge number means? More than 100,000. Because this is really high tech. Why? Because silicon carbide, our processing temperature is 2,500 degrees C. All the silicon quartz, they melt. So you need to special for annealing. And also to observe all this stacking force, they are nanometer. Actually, 1 nanometer. We have a lot of high tech. So I think we will create a lot of high talent of a professor and a lot of academician. We actually have a huge job to do. We need to examine every wafer because one wafer costs $30,000. Why not to check? Okay. And you will get this reason. Even you can form a company to do the defect check, become listed. Thank you.
Yes, and actually it's cross-disciplinary. So, I mean, it's not only that it's an electrical engineering PhD, it's material science, it's physics. There's also elements of artificial intelligence, machine learning. So it's, I think it has a lot of expertise which is required to be developed if you want to build up the talent pool for this. Thank you.
We are running out of time, but just one last question I would like to go for it. And to all panelists whom I would like to take this, I would like to go straight because when I'm talking about setting a fab, the two aspects come into the picture, return on investment particularly. So the size of volume of the fab, what should be it for the kind of a return or investment which has been done over it over the period of time. Say it's GaN on silicon or a silicon carbide of 6-inch size. Or I would say that substrate size shall also be a bigger to play a role to scale the economy of return on investment. What would be your suggestion, sir?
I have a comment on that. So just looking at it from far, this is, as far as return on investment, subsidies, government support, the most spoilt industry in the world. I've never been in a situation where I have to invest in something and every bit of competitor, you're scratching your head in, if I'm going to spend $100 and the government is going to support me with $50, I'm not worried about actually having the best plant in the world. I'm worried about in the next jurisdiction if somebody is going to support my competitor with $98 of subsidy because the return on investment on the plant has no meaning. That's my outside-in view. I'm just trying to put that in very frankly. From what I saw, the whole situation comes back to something very old school. The whole situation is you have to have an extremely good skilled team who can give you a very high yield. You have to focus, just like old school business, on getting innovation, cost saving, getting your brand out there, getting products made, making an ecosystem, and getting a sort of a proper top line in place, which is no different from anything else. So that was just my 2 cents on what the right return of investment should be. It's just very questionable about what the real investment is given the different sorts of subsidies this sector sees around the world. That's my bet.
Yeah, maybe I will approach this a little bit differently. I mean, when I look at, for example, silicon carbide, when you look at the cost of a silicon carbide device, I mean, I would divide it into 3 segments. One is the material, the substrate, and epitaxy. One is the actual foundry, the fab. The other one is the packaging. So when we look at really, how do we deliver the most optimal solution, as a country, we will have to focus on all 3. And this doesn't not mean that it can be only one company which can do it. It would need the collaboration between academia, the government, and the industry. And then all of this does not make any sense. Still, you can convert this into a system, a product, and you have demand. Yes, if you can do this mega EV chargers, that is, you're creating demand. But somebody has to design the system. And so when I look at, how do we create a sustainable business, and Darshan, to your point, I mean, it cannot, yes, today we need that to get the business started, but you need sustainability, for which you need to get the complete ecosystem from demand generation to the system or product development, all the way backward integrated to the material. And I think with silicon carbide, there is that opportunity in India. I think we can look at addressing all those aspects so that we can create a really sustainable and competitive, semiconductor business in India on silicon carbide.
Quick question to you. What are the R&D opportunities in wide bandgap or ultra wide bandgap semiconductors for India, which India need to focus on? Rohit?
For me?
Rohit.
Sorry, what is the question?
What are the R&D opportunities wide bandgap semiconductors India need to focus on? Either it is a wide bandgap or ultra wide bandgap materials.
Yeah, so those I think we can, I am happy to discuss offline.
Sure.
Yeah.
So due to the paucity of time, we need to stop it now, this panel discussion. The takeaway message from here, opportunity is there, market is there, and it is going to be growing just like anything. And of course, we need to focus on the all verticals of compound semiconductor areas where we used to call it wide bandgap semiconductor material, either is it GaN technology or silicon carbide technology. Of course, we also need to focus on ultra wide bandgap semiconductor or gallium oxide, as well as, I would say, BN materials also. That would reshape our career in future. And of course, government has put an ecosystem already, and we all are set to go to the next level. Sorry, Vivek.
No, just one point I wish to emphasize again. There was also a question, silicon carbide and gallium, very well from the manufacturing point of view. But if we look again, and I again emphasize and request that like the panel we are having, which is more a little bit focused on manufacturing, we should also have the panels, such kind of panels on system design for silicon carbide and gallium nitride. Gallium nitride system design we can do even now, right? Because it reduces form factors and all that, because that piece is a very important one. That's why I took the opportunity to emphasize on it, because without that, our ecosystem will not complete. And so the demand side of any project is very important. Where is the demand of my project? Unless that we fix, it would remain very critical. So therefore, my request, appeal would always be, let's not forget system design of these components. Thank you.
Thank you. One or two quick questions if we can take, sir, if time allowed. Okay, so we can take the questions of the dais. And thank you, panelists, for your enlightenment on the subject. And we are really appreciating your time, sir. Thank you, and Jai Hind, and good evening.